Um, Good morning, dear students. We are trying to go the old school way by recording the video and then I'll upload it. So in today's DPC4 or IIS4 class, we are speaking about chapter 3 of our textbook, which is one of our textbooks. I'm referring here to programmable logic controllers. And this chapter is about revision of digital systems. It's about revision of digital systems, and for that matter, it will be accompanied by a couple of other chapters from digital fundamentals, which is another textbook that is actually used in Digital Systems 1, and it's written by Thomas Floyd. A copy of this textbook will be uploaded on my tutor for you to use, and the different chapters referred to here will be pointed to through a WhatsApp text that I will provide to you. Okay, but we start with the content of our digital systems chapter within the programmable logic controller textbook, which is the prescribed textbook. So just very basic element of digital systems, and maybe before we start by a quick motivation as for why we need to revise digital systems when studying about digital process control or when manipulating a PLC. You recall that a PLC is a digital processor, or contains a digital processor like any other platforms that we discussed that could be used as an alternative for digital process control. We had mentioned microcontrollers, microprocessors, etc. So, as being a digital processor, a PLC is therefore capable of performing logical as well as arithmetic operations. Logical as well as arithmetic operations. And when it comes to logical operations, these refer to the process of ANDing, ORing, noting or inverting. And as we know from Digital Systems 1, those three, ANDing, ORing, and inverting, represent what we call basic logic functions. From those three, we have what we call derived logic functions. And these include XORing. You can think of XORing, you can think of NORing, which is a combination of ORing and noting or inverting, NANDing. And this can become more and more complex. And as it becomes more and more complex, you can get as far as very complex logic functions, which can be categorized into two. We can have what we call combinational logic functions on one end, and we can have what we call sequential logic functions Okay. And as an example, before we dive into the core of the subject, let's look at combinational logic functions. If we look at what we refer to as combinational logic function, the keyword here is combinational. And combinational simply means comes from the combination of couple of logic gates in order to perform a logic function. So this comes from a combination of logic gates to perform a logic function. And most of times to model a combinational logic function, we often use what we call a Boolean expression. And a Boolean expression, to represent a Boolean expression, we need to first of all understand what we call a variable, what we call a literal, and all of these are concepts that you've learned in Digital Systems 1. So when it comes to the concept of a variable and a literal, what is a variable? A variable in a digital system context is a letter of alphabet. It's a letter of alphabet, often a capital letter, that we often use to represent an input or output to a logic gate. Okay. A literal, on the other hand, is also more or less the same thing, but to the difference that it can represent the input or output, but it could also represent the complement of these. Meaning, by complement of these, we simply mean the inverted version of that specific input or output. So an example of a variable would be, an example, you can please hold on for me. An example of a variable would be, if we think about variables, an example will be A, B, and these will be, or C, these will be possible variables to an AND gate, for instance, whereby A and B are the input and C is the output. When we speak about a literal, on the other hand, that will be A is still a variable and a literal, but A bar is also a literal, but it's not a variable. It's the complement of a variable in this case. So in short, what we are trying to say is that all variables are literals, but all literals are not variables. Because when it comes to literals, we've got complements of variables which forms part of literals as well. That concludes that aspect. So when we speak about a Boolean expression, we're referring to that specific letter representing the output of the logic circuit, followed by brackets and what we call a domain. A domain is a list of all variables that appear in the logic circuit or in the logic function, in this case Boolean expression in this function, in this case, sorry, whether in complemented or uncomplemented form. So that set of variables that appear in the logic function or circuit, whether in complemented or non-complemented form what we call a domain. So if we are to refer to the domain of F, that will be A, B, C, because it's a set of variables that appear in the Boolean expression of that specific logic function. So now that can be described, for instance, as A bar B plus B plus C bar, and we'll say the domain of this function F is ABC, set of ABC. As you can see, all the possible variables that appear whether in complemented or non-complemented form in F are A, B, and C. So that specific Boolean expression, as you learned in Digital Systems 1, represent a logic circuit, which is in this case a combinational logic circuit, that you draw as follows. You have an input A being complemented or inverted to give A bar. We've got an input B being ended with A bar, and then the output is ORed with B, right, to produce A bar B plus B, and all of that is ORed with another input C to produce F. So that will be the logic circuit, which is combinational in this case, because it comes from a combination of logic gates that will represent this specific logic circuit. So now when we refer to sequential logic circuits, on the other hand, these are logic circuits that involve the concept of time and the concept of a clock. So as you can see in this combinational logic circuit, a change in the input more or less automatically result in a change in the output. Okay, so we assume that there's literally no time between the input side and the output side. A change in the input side affecting the output value. So if A was to move from a logic of 0 to 1, that automatically reflects into F. F changes accordingly, more or less in no time. But when it comes to sequential logic circuit, which is the other category of digital or logic circuits, which are circuit implementing logic functions, we have the idea that there is, as the way sequential insinuates, there is a present Boolean value and a previous value. And these are logic values or Boolean values. So the sequential logic circuit brings the idea that there is a present value of an input or an output and a previous value of an input or an output, that both are used to define the logic circuit. So that automatically brings the idea of what we call memory. So the idea is that we, in order to define a specific output, we just don't use a present input. We can also make use of a previous input. And such circuits, although built from logic gates, because the logic gates present the foundation of logic gates present the foundation of any logic circuit. Although built from logic gates, they come with some specialty, and that specific aspect of it is what we call feedback configuration. And what feedback configurations bring is basically that idea of memory. So a typical sequential logic circuit would be a flip-flop, for instance. Flip-flop circuit. And you recall that at the block diagram point of view, we'll represent a flip-flop with a clock being fed, a block diagram with a clock. Let's speak about the JK flip-flop, which is named after John and Kilby, which are the names of the inventors of this specific device. It has got an output Q and Q bar, which is the complement of the output. You'll recall this from Digital Systems 1. But now, what is the clock bringing in the whole concept? Why do we need a clock? Because remember we said there is now an idea of time, because there is a previous and a current state of an input or of an output. But where is time coming from in any digital systems? For those who did hardware design with me, I had already taught you, and this is a concept that you are most probably familiar with, whether you are busy with hardware design now or whether you've done it already. From a general point of view, in a digital system, what brings the concept of time is another reference signal that we call a clock. So it's when we speak about a clock that we can start speaking about time in the concept of a digital system. And a clock, as you know, it's that reference signal oscillating at a certain frequency, which is of course equal to the inverse of the period of oscillation, that defines therefore the minimum duration interval within that specific digital system. So for instance, a microcontroller will normally be interfaced with a clock. We sometimes use a crystal clock, which could be internal or external. That applies, the same concept applies to a PLC. A PLC is also having an internal clock that defines the concept of time. And how is the concept of time coming into play? Because what happens is that now every operation that gets performed by the CPU of the PLC will be defined in terms of what we call a machine cycle. And that machine cycle will be defined in terms of a certain number of clock pulses. And therefore, if an operation, for instance, takes 2 machine cycles to execute, of the CPU to execute, and every this CPU is interfaced with a clock, an oscillator running at a frequency of, let's say, 1 Hz. This is just an example. It's not very realistic, which means the period is of 1 second. That will mean that that's a specific operation that takes 2 machine cycles to execute will take about 2 seconds to execute. So that's how the concept of time comes into play in any digital system. So you recall the concept of flip-flop. The flip-flop, in the concept of flip-flop, previous and next state will be defined as the state of the input or output on this present clock age, if we refer to different clock ages, with respect to the present of the state of the input and output of that very same flip-flop on the next clock pulse. Is that okay? So the clock pulse at which we are defines whether we are in a context of a current, defines what is current and what is previous, or what is next in terms of the different states or logic states of the input and output of the flip-flop. Okay, so that comes in, you find the concept of flip-flop in the textbook on page 75, and in the other textbook I'll provide to you on my tutor. That concept is also clearly highlighted, and that comes with the feedback configuration, as we mentioned. And the general circuit that shows how a flip-flop is built from basic logic gate will be drawn just now. I'll just draw it now, just to show the idea of feedback configuration and how that allows for memory to be created within the logic circuit. Okay, my internet is a bit slow. I'm just trying to open up the textbook that I referred to, Digital Fundamentals. Okay, one moment. So a flip-flop, JK flip-flop for instance, can be designed using either a NAND gate or a NOR gate. The two lead to the same logic. We'll quickly wait for it to open. Okay, internet is really bad. Okay, let's see. Maybe change of strategy. Okay, hold on for me, please. Okay, yeah. So let's take the case of a flip-flop built from NOR gate. So in the case of a flip-flop built from NOR gate, we'll have that first NOR gate, second NOR gate, providing Q and Q bar. The feedback configuration I was mentioning is that the output of the one gate serves as an input to the other gate, and so on. This is what is sometimes referred to as the chiasma configuration. And from there, we have the two inputs. There we could have our J as well as our K input. But often, all of this has to be coordinated through an AND gate, just to allow for the clock, for instance, to play a role. So normally you would have your J input there, then you'll have it ended with the clock, and then you'll have another NAND gate going to the K input, just to show how the clock it serves as a gate basically to allow at what moment J or K will have an impact on the output. But if we were just to focus on the part without the clock, which is actually called the latch, that's a SR latch, you will see that there is feedback of the output to serve as an input to the gate, and that idea of a feedback in the chiasma in this case is what brings the concept of memory in a sequential logic circuit that a combinational logic circuit does not have. Okay, that one aspect. But before we move any further, we now have an idea on the two major types of logic functions that we can expect to be performed by a PLC, which are combinational on one end and sequential on the other end. Of course, there are many applications of sequential logic circuits that we also learn in Digital Systems 1. These include latches that can be used to debounce a switch, flip-flops. Among the different functions or core functions of a flip-flop are counting. Digital counters can be built from flip-flops, and in our PLC programs, we will actually design actual counters sometimes, and we also use a counter block. A counter block is already what we call a functional block, an existing block with all the basic low-level implementation in terms of flip-flop already performed, and we just have to configure it and use it in our PLC program. But when it comes to the underlying concept behind it is what I'm referring to here, the flip-flop applications that you learned in Digital Systems 1. But before moving any further, and that's where I should have started maybe, is a quick revision of the concept of digital systems itself, the type of numbering system used, because remember we said a PLC is a digital processor, so it performs not only logic functions, but also arithmetic functions. And to perform arithmetic functions, these need to be performed on an actual number, right? Therefore, we need to understand how number systems work within a digital system, of which a PLC is one. And these are concepts you are used to, but we're just gonna quickly revise. So let's start with what we call the binary system. Because remember, digital systems comes from the concept of the philosophy of Boolean logic. And when it comes to Boolean logic, it's all about, at a philosophical point of view, it's all about true or false. So the idea is that a statement or a proposition is either true or false. And from that true or false, digital systems was born. The Boolean logic refers to what, from Boolean logic was born a binary number system, as a number system to count in terms of Boolean logic. And that refers to a true as a 1 and a false as a 0. Like any number system, like the one we're used to, decimal number system, which comes from our digits. We've got 10 fingers, and people used to use their fingers to count. You must have a number system. So decimal, which is the number system we are mainly used to, has a base of 10. and those are the 10 digits of a hand. Binary number system, on the other hand, has got a base of 2. Base of 2, because it's based on the fact that something can either be true or false. Only 2 possible states. And therefore, like in the decimal number system, where the base being 10 led to 10 digits, which ranged from 0, 1, 2, 3, 4, all the way to 9. In the binary number system, we go from 0 to 1. Only 2 states, because the base is 2. Now, the binary number system is the number system in which digital processors work. However, it's not a very familiar type of language that a human being, a normal, typical human being will understand. Therefore, it's important to learn other number systems that are used or invented with the purpose to just alleviate the challenge posed by the binary number system, and very important, how to convert from one number system to another, because that's exactly what happens if I am to implement a digital process control. I'm trying to control maybe the angle azimuth at which my antenna turns. I need to be able to input that value as a decimal number. So I want to turn the antenna at 30 degrees. So I'll normally put 30. But 30 needs to be converted in binary by my, because in binary number system, so that my digital system or processor, which is the PLC in this case, can understand it, because it works in binary. And after it has performed work on in binary, it has to retrieve it back into decimal number system, so that maybe for display purposes or anything like that. So that highlights, in short, the importance of conversion between the different number systems. And we will focus here on binary, octal, hexadecimal. So binary number system has a base of 2. Octal has a base of 8. Hexadecimal has a base of 16. And we're going to look at other encoded number systems, such as gray code. What is gray code and how is it? How can we move from binary to gray or gray to binary? BCD, or binary coded decimal number system or coding scheme, and many other are also revised in the digital fundamental textbook. But how do we count in any of these number systems? Let's start with the binary number system. The decimal number system, sorry. We will normally count from 0 to 9 across or through all the 10 digits. And as we carry on, we start having a combination of 2 digits, then 3 digits. And as we move on, that's how we move forward. In binary number system is very similar. We go from 0 to 1, then we have 1 0, then 1 1, then we go to 1 0 0, then we move from 1 bit to 2 bits to 3 bits to 4 bits, etc. 1 0 1, 1 1 0, and 1 1 1, etc. Is that okay? So that's how we count in binary number system. When it comes to octal, it's more or less similar. You go from 0, 1, up until 7, which is the last digit. Then we go back to 1 0, which will represent 8, basically. Then you've got 1 1 till 1 7, sorry, 1 7. Then you go back to 1 0 0, etc. And hexadecimal goes the same. It's base 16. The digits go from 0 1 to 9, A, B, C, D, E, F. So A representing 10 in decimal, F representing 15 in decimal. So we should be able to convert between the different number systems. We should understand the concept of binary coded decimal. I think I'll jump to that, because the other one you'll do as self-study. Let me jump to binary coded decimal. What is binary coded decimal? A binary coded decimal number, BCD number, is a number obtained, as the name says, binary coded decimal. So you take a decimal value, let's say 47, and you represent each of its digits as a 4-bit binary number. Then you get a BCD number. So for instance, 47 being a decimal value will translate in BCD as, we'll have to write 4 as a 4-bit number. That would be 0, 1, 0, 0, and 7 as a 4-bit number will give 0, 1, 1, 1. So if we put the two next to each other in their order of significance, so 4 first, then 7 later, and that as a BCD code represent 47 in decimal. That's how BCD works. When it comes to gray code, on the other end, it's a very important code used in digital systems with a lot of applications, namely encryption and others. But how does gray code works? I'll just show you binary to gray code conversion as well as gray to binary. Let's start with a binary number, for instance, that. How do we convert it to gray? We drop the most significant bit, which remains the same. Then, to convert it to gray, we XOR 2 consecutive bits each time to generate the next bit. 1 XOR 0 gives 1, 0 XOR 1 gives 1, 1 XOR 0 gives 1, 0 XOR 1 gives 1, 1 XOR 0 gives 1, 0 XOR 0 gives 1. And that is the gray code equivalent of that binary value. All right. Sorry, 0 XOR 0 gives 0. I made a mistake there. Okay. That will be the gray code equivalent of that specific binary value. And to move from gray to binary, it's kind of similar. You drop the most significant bit, which remains the same, but you XOR bits diagonally now. 1 XOR 1, which gives 0. 0 XOR 1 gives 1. 1 XOR 1 gives 0. 0 XOR 1 gives 1. 1 XOR 1 gives 0. 0 XOR 0 gives 0. So as you can see, you can move by using the XOR operation, you can move from binary to gray and gray to binary. And that also is part of revision. But now, as we mentioned, and now moving to number systems again, as we mentioned, a PLC has an ALU, a CPU which has got an ALU, so it's capable of doing both logical as well as arithmetic operations. When it comes to arithmetic operations, we need to it performs them on numbers, obviously, and these include addition, subtraction, multiplication, division, and other derived. Those are basic arithmetic operations. And other derived arithmetic operations. The other derived arithmetic operations can be as complex as logarithmic, exponential, etc., sinusoidal, etc. But the PLC is capable of those arithmetic operations. But arithmetic operations are performed on numbers, and these numbers manipulated are in binary format. So for us to understand the binary number, for us to perform arithmetic operations properly while writing a PLC program, we need to understand the number systems on which they are performed. And for that matter, we're going to learn about how we sort of learned already how positive numbers are represented in different number systems and how to convert from one to the other, binary to decimal, decimal to binary, hexadecimal to octal, octal to binary, etc. We should be able to do that, and I highly encourage you to revise that through the textbook I'll upload and in your own time. But now, we know very well that some of the arithmetic operations involve what we call negative numbers. Now, how does the PLC handle negative numbers? For that matter, we learn about what we call signed numbers. Signed numbers, and this once more is still a revision of digital systems work. When it comes to signed numbers, you learned a couple of formats. The one was the sign magnitude format, in which one bit was dedicated, mostly the most significant bit, was dedicated for the sign. And when it was a 1, it represented the negative value. And when it was a 0, it represented the positive value. positive sign, basically. Sorry, sign. And this comes from the fact that minus 1 to the power 1 will give you minus 1, while minus 1 to the power 0 will give you 1, which is a positive value, therefore. And the rest of the bits, so we've got the sign bit, the rest of the bit will represent the magnitude. So in that case, if you had a 4-bit signed magnitude number, let's say 1, 1, 1, 1, being a 4-bit negative number in signed magnitude format, the one will show that this is a negative, is a binary number. The one will show that it's a negative number, that's a signed bit. And the other 3 will be the magnitude, which is 1, 1, 1, 1, in decimal will represent 7. That will be minus 7. Will be understood as minus 7 by the PLC. But now, if we move on to other for representation of negative numbers in digital systems, we have what we call the ones complement. Ones complement. And ones complement of a number is a concept that says if this specific number, let's say that's a binary number which represent 0 plus 0 plus 4, 4 plus 8, 12, 12 plus 16, 12 plus 16, which gives 28. So that's 28 in decimal. So if that represents 28 in decimal, its corresponding negative number, which will be its complement, basically, which is minus 28, can be obtained by just reversing or complementing these every single bit of the value of 28. So you just complement that, you get 0, you get 0, you get 0, you get 1, 1. So that would represent minus 28 in a first complement format. But that specific model was not very helpful because that could be confused with a value of positive 3. So therefore was invented another representation of negative numbers in digital systems, which is called 2's complement. And that's the most commonly used representation of negative numbers in any digital system or platform. And that is obtained basically by just first getting the ones complement of the number and adding 1 to it. So that would be 0, 1, 0, 1, 1, 0, 0. So this specific value will be minus 28 in 2's complement format. 2's complement format. Right. Will be minus 28 in 2's complement format. Okay. That has covered signed numbers and ones complement in the textbook. Floating point numbers. What is the concept of floating point numbers? Before we discuss floating point numbers, let's consider fixed point numbers, because when it comes to processors, they come into 2 formats. We've got fixed point processors and we've got floating point processors. All of these concepts are clearly and more in details highlighted in hardware design 4. But the idea of a fixed point representation of a number in a processor, a digital processor, of which the PLC is one of them, has to do with the fact that there is a fixed size of memory allocated to represent that number. While in the floating point case, the number is represented in terms of a mantissa, an exponent, and a base. So, for instance, in fixed point, a decimal number of 1,23 will be represented like that. But in floating point, that could be written as 123 times 10 to the power minus 2, for instance. What is the difference? Is that here you would store the exponent, the sign of the exponent, the base, as well as the mantissa. Mantissa, exponent, sign of exponent, base. Those will be the values to be stored. But instead of storing 1.23 in a fixed reserved amount of memory space, you would save those sign of exponent, exponent, mantissa, and base. So those 4 elements, and that will represent the number. What is the benefit of a floating point number is that you've got more accuracy and you've got more precision compared to fixed point. Because with fixed point, the size allocated to represent the number being fixed, you get to a point where you cannot be very accurate, especially on numbers that do not the number of decimal numbers with values after the comma not ending, meaning a continuous set of values after the comma, or becoming more and more, you get to a point where the number gets truncated and you lose some accuracy. And this once more is a basic concept that is also learned in Digital Systems 1. But why did we have to revise Digital Systems in studying Digital Process Control 4, where we manipulate the PLC? This is simply because when we speak about a PLC, we've looked at the hardware, the input, the output, etc. Now we must also speak about the data, because at the end of the day, the control function being performed by the PLC is being carried on a specific set of data. And that data we're referring to here is of digital nature. Okay. So when it comes to PLCs in general, most PLCs operate on 16-bit word. That simply means at a memory point of view, the word length, what we call word length from digital systems or hardware design, the processor manipulates in terms of does calculation on, or stores or retrieves data as a chunk of 16-bit at a time. That's what we call a word, or word length of a process. And in terms of a PLC, most of PLCs operate on 16-bit. All right, and therefore, in terms of the different data types that we encounter in most PLC programming languages, we will have them on 16-bit long, either integers, or we could have unsigned or signed integers, or double, unsigned double or signed doubles, and that we tend to operate on 16-bit. Okay, we'll get more in depth about data types as we manipulate and write programs. Combinational logic circuits, I've mentioned them. Sequential logic circuit, I've mentioned them already and explained them. That's where I started. But I think it's very important to also revise some basic concepts of digital systems in terms of analysis of logic functions. As you analyzing a combinational logic circuit, as I mentioned, you have to use a Boolean expression as a way to represent the logic function. The other tool that is very important in the analysis of a logic function is what we call a truth table. And a truth table is a table that on one side has got inputs, one or more, and on the other side has got outputs, one or more. And the inputs, let's say, depending on how many there are, let's say in this case we've got n equals to 4, which is the number of inputs, are set up in terms of all their possible combinations. And the number of total possible combinations, logic combinations, of course, of inputs given their number n is always 2 to the power n. So for 4 inputs, you would have 16 possible combinations. And you recall this from digital systems that as you go from the least significant bit to the most significant bit side, you will go 0, 1, 0, 1. And the next column, you're going to have 0 repeated twice, 1, 1, 0, 0, 0, 4 times, 1, 4 times, 8 times, 1, 8 times. If there was more, 16 times 0, 16 times 1, just as a way to dress up a truth table and establish all the possible combinations. In terms of the outputs are defined for every possible combination, and that has to do with the logic function being implemented. Often what we do is we go from what we call a word problem. So you're given a word problem in terms of the logic operation of a plant, for instance. For instance, this valve must open, then if only that valve is open and the second valve is open, then, for instance, the buzzer must produce a sound. That's just an example. In that short and very concise word problem, you will identify that there are 2 inputs, which are 2 valves, and there's one output, which is the buzzer, where the buzzer is connected, basically. And you would establish that if a valve being open produces a logic of 1, for instance, and the valve being closed produces therefore a logic of 0, then if we say that the buzzer will ring if valve 1 is open or valve 2 is open, then we're talking about a case where we have a logic 1 on either of the input. Is that okay? This leads to the digital systems concept of what we call sum of product and product of sums that you also have to revise. When we speak about a Boolean expression, we said that they could be represented in terms of SOP and POS, and this could be a simplified version or a standard version. And by standard version, we simply meant that was the version of the representation of the logic Boolean expression where in each term there is a representation of all the variables of the domain of that Boolean expression. But as in the simplified version is the smallest format of that Boolean expression, that to make the implementation use less logic gates and be therefore less spacey and less costly because of the fact that it uses the least of gates. And we learned a lot about Boolean algebra in Digital Systems 1. We learned about Boolean algebra, and in terms of Boolean algebra, we learned about how to simplify a Boolean expression, meaning moving from a standard to a simplified version. There we learned about the 12 rules of Boolean logic that you find in the textbook and that you have to revise and study yourself. Then we also learned about the theorems, Boolean theorems, and here we had learned about two specific theorems, and those Boolean theorems, as you recall, were used to convert from a NOR gate to an AND gate on one end, and we had a way to convert from a NAND gate, therefore, to a NOR gate. To a OR gate. So from a NOR to an AND, and from a NAND to a OR. And those were a couple of the things you learned in Digital Systems 1 that I'm trying to revise with you here. And I'll point you exactly to the different textbook digital fundamental pages that you need to go through as a revision of this chapter. That will conclude our class on Digital Systems 1 revision, but I'll conclude it by pointing you out to, in a WhatsApp message, to the different pages that you need to go and revise in terms of SOP, POS, and as part of this effort to simplify a Boolean expression, we also learned about what we call the Carnot map. Carnot maps, and when we learned about Carnot maps, we learned about them as a simplification technique for a Boolean expression. And the steps were simple. You first go from a problem given in Word, you translate it in a truth table. From the truth table, you dress up a Carnot map, then you do grouping of cells, and based on a grouping of cells, you can simplify the Carnot map to produce the simplest form, SOP format of the given Boolean expression of given logic function or the simplest POS. Depending on whether you group ones or zeros, you can produce a SOP, simplest SOP or simplest POS. I highly encourage you to revise that, and you'll be given an opportunity to ask questions with respect to that. So in the textbook called Digital Fundamental, that normally appears on your my tutor. If not, I will have to upload a copy of that, and I'll also share it on WhatsApp group. You will basically have to go through more or less the whole textbook, but of course that's more or less impossible. I'll just quickly highlight maybe the key aspects that you should focus on. We shouldn't waste a lot of time or spend a lot of time on this chapter 3 because it's a revision chapter. In some of the semesters, I literally just made it a self-study chapter, but I thought it was important to sort of give you guys a quick background about this. I'm opening up the textbook. The textbook, I'm also sharing it in your folder on my tutor. One moment. That will be available in few seconds. Okay. Nope. I have to go inside, and just gonna move that to the my tutor folder. Move. Okay. The DPC store, and we go to content. Content. In terms of content, we go to semester 1 2020 books and handouts, and I move it there. That will be moved there. We also I'll also move it to the IIS group folder so that we can have access to the same textbook. Come here and I say okay, and go to IIS in this case. IIS, and I go to the folder with 2020 first semester content, books and handouts, and there it is. So the textbook is now available on my tutor in the right folder. So at the same time, we also have it shared with you guys. I'll have it shared on my on WhatsApps just now. It's taking long to open because my internet is quite slow. Okay, just save as. Let's see. Well, I'll share that. Thank you guys. That concludes chapter 3, and we'll carry on for the other part of the today's class.